Okay. Thank you. Thank you for that introduction. Yeah, and thank you for everybody who's here today. I'm excited to talk about the Merdeka 118, or for my colleagues who worked on this project, the KL118, as it was referred to. This project is especially exciting because some of the new ways it spurred innovation and ultimately optimization of mixed designs used to build this high rise. As mentioned, my name is Steve Herald. I'm out of Denver, Colorado. I work for Aggregate Industries, which is part of the Holcim group, LafargeHolcim, known around the world. And I've been, like I said, for 24 years. And I am currently in the Technical Services Manager role out there as we're delivering to the Denver market and up and down the Front Range. Quick note before I jump into this. I want everybody to know here that this tower is an amazing tower. I wish I had firsthand experience working on this. I'm building on some of the backs of some great people that worked on this project. And I had the pleasure of working with a couple of those folks actually in the last 4 or 5 days on we're bringing some of this technology to the state. So, and I'm excited to talk about that. Okay, so real quick, Holcim, a global leader in building materials and solutions. We are active in all 70 or around the world in 70 countries. We have 72,000 employees in our business. We are active in cement manufacturing, aggregate manufacturing, ready-mix concrete production and delivery. And we have a research center in Lyon, France, that is dedicated to solutions and products. And additionally, one of the first global companies to sign up with the UNGC's business ambition for 1.5 degrees Celsius initiative with 2030 targets. I'm going to cover this project today in about 4 phases. Please note that this project is, again, too large and complex to talk and cover in 20 to 30 minutes. So I will discuss just a couple key topics in the design and construction of KL118 that were critical to the project's ongoing success. We're going to look basically at a quick project overview, a quick construction timeline, and the high performance concrete timeline, and then key design and placement challenges. The ultimate goal of this presentation is to show how the design requirements for the project, the unique requirements to go to the heights that we were having to get to, forced optimization of many aspects of the process and the material. So some key facts about KL118. It's located in downtown Kuala Lumpur. It's 118 floors, 2,227 feet tall, and has a 520-foot tall skyscraper or spire. When completed, it will be the second tallest tower in the world when you count the spire. It is a mixed-use high-rise with a hotel, office, and retail space, and it will host the new headquarters of PNB. It's a LEED Platinum project, and the construction of the Merdeka PN118 tower has an estimated cost of US $1.5 billion. The owner on this project is the PNB, Malaysia's biggest fund management company. The designers, FK, an Australian architecture firm, designed the building. RSP Malaysia is the architect of record. Arup and Lara are the engineer of record and structural design. Lara is a global reference and structural design firm for high-rise buildings around the world. And the main contractor, which was Lafarge Malaysia's client, was a joint venture between Samsung and UEMC. Samsung C&T has been in the construction business for over 38 years, and Samsung was the joint venture lead on this project. They have built iconic skyscrapers such as the Burj Khalifa in Dubai, which is 2,700 feet high, highest in the world by far. And additionally, the Petronas Twin Towers in Kuala Lumpur at 1483. And during the proposal phase, Samsung C&T proposed value engineering solutions that help the client to reduce costs. And we're going to talk a little bit about that as we go through the materials. And on February 12th, 2015, Lafarge Malaysia signed a collaboration agreement with Samsung for this project. The concrete was key to winning the project for Samsung, and the modulus of elasticity was key to making this design work. As part of this agreement, the local Lafarge team designed, tested, and supplied all the concrete for the tower. The mix optimization and development took place in 2015, and the project concrete volume tipped out at 390,000 cubic yards. Several different classes of mixes were required on this project, 14,000 PSI being the highest, and that covered basically from level 9 to the roof, and then level 9 to level 78 of the core walls. And we're going to talk about the mega columns and the mega core walls here shortly. And then the 12,000 PSI covered the basement level 4 to level 8 of the mega columns and the core walls. There were also 9,000 PSI designs, and one of these designs covered level 79 through the roof, core walls, and also the raft foundation. And it's important to point out that the raft foundation was poured in 3 castings, and the volumes ranged from 5,200 cubic yards to 13,000 cubic yards. On one particular pour, a 12,800 cubic yard placement. It was done in 28 hours with 9 pumps and 120 mixers. And then, of course, they had the 6,000 PSI mix for the tower slab, tower podium, staircase, and inner core. And all the concrete on this project was tested with 6x12 cylinders, and all cylinders were in ground for precision and consistency. The core walls, mega columns were linked by steel for the decks and intermediate columns. It was determined for the very high strength requirements that 56 days was the minimum PSI requirement, and 90 days was best, especially for the modulus of elasticity. The later age acceptance requirements became key to optimizing cost, energy, and materials. And I can't stress that enough. As I spoke to the folks involved with this project, it wouldn't have been possible to optimize the mixes and achieve what they achieved on this project without pushing out the acceptance age to 90 days in some cases. So a quick overview of the construction timeline and placement of the high performance concrete. We're going to focus, I'm not going to focus on the 6 and the 9,000 PSI. We're going to focus on the 12,000 and 14,000 PSI requirements. 12,000 PSI concrete was used from the basement through the 9 first floors for the core wall and the super columns. And I don't know if you guys can see, but the core walls, you can see there's 8 of them surrounding, or we got the core wall in the middle, and you got 8 of the mega columns surrounding the core wall. The core wall was a diamond shape. It was determined that that was going to be the best to withstand the wind shear and the wind resistance for the project. And as the project came out of the ground, those mega columns were linked to the core wall with steel for the deck placements as they went up. 14,000 PSI concrete, again, was used from the 9th floor to the 87th floor for the core wall and mega columns. And the formwork was a self-raising Doka platform with hydraulic jacks. The formwork was all steel, and placements were on a 5-day sequence between lift reinforcement pouring and the next lift. And this required 3-day high early strengths on these mixes to keep the formwork moving, which is also quite impressive when you have all the other restrictions that you're going through on this job. So the picture on your left is April of 2019. You can see the core or the mega columns on the outside going up, linked with the decks and the core wall in the center. And then fall of 2020 is the center picture. You can see they're getting close to topping that out. And then the current picture in March of 2022. The job isn't 100% completed yet. It will be in 2022. That's showing that they got the spire installed. Okay, so some key technical challenges for the high performance concrete. So we're going to talk about 4 main technical, there were 4 main technical challenges. We're going to focus on challenge 2 and 4 on this slide, but it's also important to discuss the thermal challenges briefly. The thermal plan indicated that the mass concrete for the mass elements on this project, the core wall and the mega columns, that they needed to be below 167 degrees max because of the sheer mass size of those placements. To achieve this, hot block trials were conducted to confirm the peak temperature was less than 167. Full-size 70 cubic yard mock-up trials were conducted to measure temperature at pouring time, peak temperature, and temperature gradient within the structure. And because the core walls and mega columns were so large on this project, they were monitored wireless with real-time sensors that kept the Samsung team keyed in at all times. So they could see on their phone what was happening in real time at any time of the day. They had wireless sensors running. The concrete batching, as you can imagine, with some mass placement such as this, was critical. There were obviously the temperature requirements. To achieve the max temperature of 167 with these high strength mixes, the concrete batch or the plant itself used ice feeding the plant. And in some instances on the very critical placements, 100% ice was used for batching, no batch water, just all ice. And to feed that, they had an ice plant basically built and set up right next to the ready mix plant on site. So the temperature requirements aside, we're going to focus on two key challenges related to the design, and that is to achieve the mechanical properties, the elastic modulus, and the compressive strength. And then again, the rheology and pumpability properties that allowed them to be pumped up to the tower at 1,700 feet. And that's really the exciting. I'm really excited about this new technology. So I'm excited to talk to you about this. Okay, so let's talk about the mechanical property challenges. Okay, concrete compressive strengths. Again, all tested with 6x12 cylinders on site. 14,000 PSI was the requirement at 56 days. And the modulus of elasticity was 45.3 GPa or 6,570 KSI at 91 days. The design that was used achieved an average of 14,500 PSI at 91 days and a modulus of elasticity of 47.9 or 6,945 KSI. So just pushing over the requirements. For the 12,000 PSI design, the project requirements were at 28 days with a modulus of elasticity of 47.9 GPa. I'm sorry, 37.4 GPA. And the design that was placed achieved an average of 13,000 PSI and 45 GPA or 6,500 KSI on average. It's important to note that because the project team wanted to exceed and needed to exceed the design requirements for the optimization of this mix to work. In order to test the ultra high performance concrete, both Lafarge and the test lab of record purchased the same high performance brake machine. It was determined early on that they didn't want to have any issues between either of the labs as the cylinders were being broke. Additionally, if you went with a standard machine, the QC manager for the project joked with me and said, if they would have just went out and bought just a random old machine, they probably would have broke it every 3 months with this strength. So yeah, again, all cylinders were end ground and to a very tight specification. All the material, again, broken on the same machine. During the lab trials for the development of these designs, it was determined that the local supply of stone was not adequate enough to achieve the high modulus of elasticity requirements. The design team then targeted a basalt ag source that ultimately improved the mixed design gradient and helped achieve the elastic modulus requirements. Additionally, the workability was enhanced. Once the gradient and the modulus of elasticity was improved, the team settled on the following materials to further optimize the mix. So for these designs, the cement was coming from LafargeHolcim in the Kathan plant in Malaysia. The slag, which was critical to the packing density and the gradation, was coming from Rizhao, China. The silica fume was Elcom Asia out of Thailand. And that material was proved to be better than the local material because it had better consistency. And then again, the key to the success of this project was the basalt aggregate. About 125 miles from the project, so it had to be imported. That's a lot of material to be imported, but it was critical to the success of this placement. or this project. Lafarge, and another key point is that no fly ash was used on any of the high performance concrete in this project. It was all slag and cement. Lafarge installed a twin shaft heavy duty mixer to cope with the high binder content of the mixes. And I'm going to show you some of the examples of how the basalt helped out with some test data here shortly. Okay, so just a real quick look at what the mix designs look like on this for this project. So you can see the 14,000 PSI, and if you're looking at this, you got the L, M, and the H, the C95L, C95M, and C95H. That's as we started to go up the tower, we had to redesign that mix for 3 different levels to get it pumped up there. So you can see water cement ratios at a 0.25 basically remain the same for that 14,000 PSI mix all the way to the top. But what you do see is the cementitious contents slightly creep up and the aggregate contents. It's quite an impressive design. So another thing to point out on this slide is I'm going to talk about the tribometer here shortly, but through this process, we identified that the admix, the super P, the high range water reducer, was extremely critical to how those particles moved and how it coated the particles in that mix. And if you use the wrong high range water reducer, they're not all created equal. If you use the wrong one, you're not going to have the right lubrication. You're not going to have the right movement, and it would make it really difficult to pump. So we came up with some new technologies that I'm going to talk about to really isolate what is going to be the best super P to use, what is the best slag to use, and so on. So the basalt aggregate, it helped us achieve the modulus of elasticities in the 6,500 KSI range. And the basalt aggregates allowed the 14,000 PSI mix to save 14,000 tons of steel, thanks to the higher stiffness. It also allowed the design team to generate 21,000 extra square feet due to the section reduction of the superstructure walls. So one of the key points about this is, if you remember, the basalt aggregate had to be shipped in from 125 miles away, significant cost to do that. That cost was about 2.8 million extra to bring that aggregate in. But the savings that they got from the reduction in the steel and the increased space is on the order of 10 to 20 million. So the point is using local materials, using the cheapest, using the lowest price point is not always going to save you the most money. You really need to do the background check on that. Okay, so now we got these high performance mixes and we're pushing them quite a ways. So there are some very unique challenges that were required, and what the Lafarge team in Lyon, France helped with this to push this out. So the pumpability of the mix designs was very critical to the success of this project. To test the feasibility of pumping the proposed mixes, Samsung set up a full-scale mock-up and pushed these mixes the distances required by the project. They lay out, I got a picture a little bit later, they laid out all the pipe to go all the way up that full distance, and they did full-scale mock-ups to determine if that was going to be able to pump. In 2015, when this project was kicking off, this was the best method for determining the pumpability of a given mix. Shortly after this project started, the Lafarge Innovation Center implemented a new tool optimized in Lyon to help simulate pumping conditions on the project. The tool is not new. The tool is the tribometer. And for those who don't know what a tribometer is, you're measuring the yield stress of a mix design. But the unique thing that the Lyon team came up with was an analyst tool to analyze the results of the tribometer. This project gave the Lafarge team the opportunity to validate the simulation tool and pump pressures measured on site. We used it mainly on this project to benchmark different admixtures and adjust dosages versus growing pumping heights. We also used the tribometer and simulation tool in order to benchmark different sources of slag. As I said, the slag earlier was critical to the workability of the mix. Okay, so this is what, for those who may have never seen the tribometer, but this is what it is. So you get yourself a bucket of concrete and you got a shaft. It looks like a drill press. You got a shaft coming down, then you got a larger concrete cylinder on the end, solid cylinder, and you're basically putting it in the mix design. You're turning it on at different velocities and you're measuring the torque. And that torque, it gets converted into yield stress calculations. And then you can take that information and start plugging in and doing some prediction. But there's a video here in a short bit that shows you this, but what you see is as it starts turning, like this right here on the left is what we call a plug flow. This would be traditional concrete. As it starts turning, you get a slight lubrication layer between that shaft and the concrete, and that is what helps that concrete push in the pump, is that lubrication layer. And as you see on the top, the majority of the inside of that concrete is plugged. It's not plugged in the pump, it's just a plug. And you're pushing it with the lubrication layer. And then the opposite, or one way to think about it is, think about it in reverse. That picture on the right is the hybrid flow. Think about it, the concrete that is touching that steel shaft is essentially touching the outside walls of the steel pipe as it's pumping. And then everything that moves out to it is moving towards the center of the pump pipe. So, and then the hybrid flow on the right, the video that didn't work, and we couldn't get it to work in the presentation, but if the video was playing, and you'll see it, the whole mixture is turning with it. So, and this was the type of mixes that were being used on the KL118 project. And you had a smaller section in the center that was your plug, and you had some sheared concrete off to the sides because of the low yield stress. And that's what helped. We monitored that type of performance by changing the slag, changing the aggregate supply, and then really focusing in on the admixtures to make sure that we had the right material to push this mix. So this is what the prediction tool looks like. You can see the red line is a given pump. So up at the top, we picked the C60/75 mix design, which we tested through the tribometer. We had the results. And then we said, we're going to push it through the HBT 9028CH pump. And we plug all that data in, the power requirements, the shaft size, all the information that's relevant to the pump. We plug that in the background. And then we put in the prediction tool. What is our elevation? 220 meters. What's the pipe diameter? 125 millimeters. And then your full length is 300. So that would be essentially 220 up and then a placing boom, right? So you have some additional resistance. And then additionally, we can also put section 2 and section 3. We can add reducers. We can add rubber pipe. You can do the tribometer test with the rubber coating and take measures of the mix as it hits rubber. And so with that information, we're able to predict. The blue line is saying, okay, with this particular mix, with this particular pump, you see the limitation of it. If you go past that red line, you can't pump it. We could tell the pump operator or the project that this mix through this pump you're going to be about almost 200 bar, and you're going to be getting about 45 to 50 cubic meters an hour without doing mock-ups. This just doing tribology testing. So as you can imagine, that's kind of a game changer. And the KL118 project gave us the opportunity to test that against real world app placements. So we were able to confirm the legitimate values that were coming out of this process. So again, this is giving you a little bit of an example. I talked about the slag coming in from China. During this project, the slag source wasn't available anymore after it started. And we started testing other slag sources, which you can see. The red on the bottom is the slag source we needed. The other sources, this is tribometer testing right here. The other sources were the ones we tested to replace it. Through the tribometer testing, without doing any mock-ups or putting any concrete in the pipe, we determined that the low shear yield stress when we used that slag coming in from China was the best solution for this project, and it helped the project make the decision to purchase super sacks of this material from China, where it was a local manufacturer reprocessed or rebagged it or put it into tankers so they can get it into our silos. But they paid that extra. They needed that material to make this project work. And we were able to confirm that with the tribometer testing. And during this project, we never plugged the pipe due to concrete. And I want to have a quick video here to play for you. This video is Fabrice Toussaint, who I got a chance to work with last week. This is how new this technology is. We're training on it to bring this tribometer tool to the US. And I got a chance to spend a week with Fabrice, who's talking on this, and Cedric, who to help create this tool.
LafargeHolcim Innovation Center has been working during 5 years on the topic of long-distance pumping. A new tool based on tribology science has been developed. It allows to predict pumping pressure. Very high-performance concretes dedicated to high-rise are very viscous and very challenging to pump at high elevation. The tribometer allows to optimize the concrete mix design, to check the pumpability, and to reduce the global cost. The tool was used to test the pumpability of KL118. The interaction with the contractor Samsung was also improved with a good level of confidence.
This is the tallest, but that's not including the spire.
We need to create a concrete that has a very good rheology, which means that in order to be able to pump it to up to about 550 meter was also in a single shot or a multiple shot it was also very important consideration that we have to have. So we contacted you here, we contacted the Research and Development Center in Lyon, and we start talking about all of these issues, how to mitigate them.
In KL118, project team did a fantastic job, and having this tool and the support of LH Innovation Center has really made a difference for our international key account Samsung. Despite having built the highest building in the world, they were really impressed by the technology, and as a result, they have asked us to expand the cooperation.
So it was really this project, the KL118, that added the legitimacy to this tool, and Samsung's desire to put it into play and to use it instead of doing these very expensive and large trials and mock-ups that really propelled this tool, and now it's being rolled out. So to wrap it up here, the KL118 project, we gained expertise on pumpability, measurement, and simulation. Building on this knowledge, we're now able to ensure pumping feasibility in challenging situations, very long distances and heights, viscous concretes, high performance concrete, and low carbon concrete. As the low carbon embodied carbon mixes, we're taking cement out, right? So we got to put other materials in, and we got to know how are they going to pump, how are they going to react without these tools were created to pump mixes with cement. And as we start taking that out, it's just changing the performance. It's also helping us avoid mock-ups, as you can see. And then it helps choose the right pump and settings for a given height. So now we can put together a mixed design submittal. We can go to a pre-con meeting. We can get involved very early in the project and say, hey, with tribology testing, we can now tell the customer, we would recommend this pump for these types of mixes, instead of just going all out and getting the most expensive pump out there. Maybe you can save the project some time and some money. And again, it helps to optimize the mix design by really looking at the performance of each individual constituent and picking the correct material to get this stuff to pump. So projects that I have either used the tribometer post KL118 or will be in the near future. The Casablanca CFC tower on the left, or over here in 2019. The Dubai towers with ABM right down here. The Monaco caissons, the precast segments to build an extension on the sea in 2019. And then the Qatar Lusail Plaza towers in 2022. And as I mentioned earlier, this tool is now being implemented in the US, and it's starting to get some traction here as well. Thank you. Yep.
Thanks, Stephen.